Hello and welcome to my channel. Today we are going to do another topic on digital logic, which is the Quine McCluskey method. It is a method used to simplify logical expressions. We are more familiar with Karnaugh map if you are a beginner in computer science course, because if you are a beginner, you are mostly learning 1 to 4 variable expressions. But for 5 expressions, for 5 variables in a expression and beyond that, it is better to use the Quine McCluskey method. Why? Because the Karnaugh map, it is a graphical method. It is the core operation of the Karnaugh map is to be grouping the similar terms in squares or rectangles. But the Quine McCluskey, it is a more computerized way to do things. Mainly, it is about the working principle. If you understand it thoroughly, it is similar with Karnaugh map, but it is in a written way and not graphical. So the core operation of this Quine McCluskey method is to group them by finding patterns. So let us go through the general step of doing a Quine McCluskey method first. Alright, on the first step, you want to write a function in a standard minterm form. What is a minterm? Let's say you have a 4 variable function here, and they are from this to all the way to here, right? And the minterm expression for this is the M0, this is the M1, and this is the M15. So there are a total of 16 different minterms. So you need to write the expression in these minterms. You want to sort them out. And the second step, you want to arrange them in groups categorized by the number of ones in the expression. So maybe you have this, so you have 2 ones inside. You have this, you have only 1 one inside. And this will be 3, a total of 3 ones. So this is, you want to categorize them into different groups. You understand why you need to do this later. And now you need to compare adjacent groups. You need to compare the categorized ones, and you need to find pattern. The pattern is you find the terms with all similar position values except for one single position. Let's say you have this, and then you have this. So they are similar in all these 3 positions except for the last one. So you want to group them to become x. X meaning that it can be either 0 or 1. So you want to express that in a x. So that's what it means by place a check mark at the differing position, at this position. You replace it with a check mark. So now these 2 expressions, they become 1. The categorized group in the third step are called the first levels. Among the first levels, you can also, using the same rule in the third step, to find all similar positions except one, and then you can group them and call them second levels. And how to do this is, let's say you have this term and you have this term. So they are similar in all 3 positions except for this. So you can group them in writing this x here. So this is the new x, this is the old x, right? So this is called a second level term. Second levels. Now at the 5th step, those first terms, let's say these 2 first level terms, are involved in making this second level term. Now you want to mark them out, you want to cancel them, and they will not participate in forming the expression. They will be represented by this one instead. And at the 6th step, you want to form expression from the first and second level terms. At the sixth step, it is not the final expression. It may or may not contain unnecessary prime implicants. Let's say in a Karnaugh map, in a graphical sense, let's say you have something like this. Typically, people will group this and this, but up to the sixth step, we may have something like this. And this third grouping, it is totally unnecessary, and we can't reach the most simplified expression if we don't remove it, right? So to remove these probable existing redundancies in the sixth step, you want to go to the seventh step and you draw a table of prime implicants and minterms. Prime implicants are the specific terms in this expression you form. These are called the prime implicants. Alright? And you need to find if any of the prime implicant is unnecessary, and about how, I will explain it later. And the last step, you can now obtain the most simplified expression. Alright, let us continue with a example. Let's say you are given this expression. It has a total of 8 terms. It is a canonical form. Canonical form is that each of the term it is fully expressed with all the existing variables in this function. Alright. A canonical form is different from a standard form. Let's say this is a standard form. This one here is a standard form. B naught C. B naught C in this expression, it can actually mean either A, D are knots, only either A or D are knots while the other is not a complement, or they are both not a complement. So it can have ambiguous meanings. It can mean a lot of terms, this one. So this is a standard form. Just some extra knowledge. So what you actually want is you need to write them in these minterms. So in our case, we can see that this is 0, 0, 0, 1, and it is M1. So you just write them in this way. Find their values. 8 plus 2 is 10. 12, 13, and 15. 15 is the largest one, the last one. Alright. Now you have their minterms. Of course, they are written in this form where the x are these numbers. Alright. Now you want to group them with how much ones is in each minterm. Let's say for M1, M1 is 0, 0, 0, 1. So it has only 1 here, as well as the M4. Alright. Which one have 2 ones? The M3. M3 here. M5. M10. And M12. The one with 3 ones is M13, and the one with 4 ones is M15. If M0 is in the given expression, there will be another category where the number of ones here is 0, and the only expression in 0 ones is 0, 0, 0, 0. Alright? Okay. Alright, now for the third step, you want to compare them and find similarities. Okay, so let's start off with the first term, M1. So you find any term with 3 similarities and 1 different position. So it is very direct that you can see that M1 and M3, where only the third position is different. So you can write here 0, 0, x, 1 is from M1 and M3. Why is this important? It is because you need to take down this position, because in the later steps, when you want to cancel out some of these terms, you want to know where they come from. You want to know what minterm they represent. So this, it represents the first and the third minterm. I mean the second and the fourth minterm. The first minterm is this. Alright, any other? Yes, of course, 1 and 5, where the only difference is the second position. So you want to put an X in the second position and you mark their origin. Is there anyone with 3 similar positions with M1 anymore? No? Alright, let's consider M4 now. 0, 1, 0, 0. So it is very direct. We can see that 4 is paired with 5, where the only difference is the last position. So you want to write it as this. Is there any other terms? Yes, the 12th term, where the only difference is the first position. So you want to write it as this. Is there any other? No, I don't think so. So now we can go on with M3. So M3 has been paired with M1 already, so we only compared with the term below it. Is there any other term with only 1 different position? No. So let's move on with M5. Note that M5 is already paired with M1 and M4, so we compare only to the position below M5. So we can see that M5 can be paired up with M13, where the only different position is the first one. So the first one you write as this X. Alright. Now we go on to M10. Is there any similar terms with 3 similar position and 1 different? No. So if a term, it cannot be found with another similar to be grouped together, it is called an essential prime implicant. In a Karnaugh map, it will be a position where it can only be grouped by itself. You cannot find 2 groups that can cover the one. So this is called an essential prime implicant. And this term, no matter how much we simplify the expression, it will stay until the very last simplification process, and it will stay there. So this is very important. You need to take note of any essential prime implicants in the process of doing this Quine McCluskey method, so that you don't forget it. Alright, let's move on with the M12. M12 can be paired with M13. Then M13 can be paired with M15. That's about all the similarities we can find here. That's about all. And then remember the essential prime implicant. Alright, let's move on with the 4th step. We need to find the second levels from the first level. So this is the first level with a similar step. Is there any other terms with 3 similar and 1 different position compared to this one? No. Let's do the second term. You can see there are no other terms having 3 similar positions and 1 different position. Let's move on. 0, 1, 0x, 1, 1, 0x. You can see that these two can be paired up. x1, 0, 0, x1, 0, 1. These two can be paired up. Alright. So 0, 1, 0x and 1, 1, 0x can be written as x1, 0x. And they come from m, 4, 5, 12, 13. As well as this one, it can also be written as x10x. And it also comes from 4, 12, 5, 13. So since these 4 terms are involved in making the second level, you want to mark them. And then this both is the same one, so they can be generalized as just this. Alright, now for the 6th step, you want to put the expressions out. Right. How do you interpret this? Say 0, 0, x1. It can be interpreted as x is the don't care term. So for a don't care term, we don't write it at all. 0 means complement form. 1 means no complement. So this is written as A naught, B naught, D. Like this, following this. So in the 6th step, there is A naught, B naught, D, A naught, C naught, D, A, B, D, and B, C naught. So you want to write them down. Alright, is something off here? Yes, you need to put the essential prime implicant, which is 1, 0, 1, 0. You need to remember that. Alright, now this is in the 6th step, you want to write this expression. And no matter how many variables there may be, there's only 2 levels we use. There's no 3rd level or something like that and on. No, we only use 2 levels. So this might still contain some unnecessary terms which doesn't contribute to or you can say the existence of this term doesn't affect the end result at all. So now you want to write all these terms as each of them is a prime implication. So prime implicant. Alright, each of them is a prime implicant. And you want to mark them at their respective minterms. So for this, you can see they represent 4 terms. So you mark them. This represents 2 terms. This represents 2 terms as well. So you just go and mark them. Alright, so now how do you want to find the unnecessary term is to see if a minterm is expressed by multiple or only one prime implicant. What do I mean by this is that you can see that M15 it is only represented by one prime implicant. So this one it is necessary. We don't want to remove this. M12 is only represented by 1, so this is necessary. M10 is only represented by this one, necessary. M4 is only represented by this one. M3 is only represented by this one. And we can see that both n1 and n5, aside from these two, we already have replacements. So you can see that this term, it is not actually necessary. So you can just go ahead and remove it. So now the final expression you want is this one. So this is how you do the Quine McCluskey method, and it is demonstrated in a 4-variable expression for the sake of simplicity. Once you understand this method thoroughly, a lot of this step, you actually don't have to write it out at all. You can just do the computations in your head, because these are all very simple computations and very direct ones. As well as this one, you can merge multiple steps into one. Overall, after you are getting familiar with this method, it is much more time efficient than a Karnaugh map, than you're trying to draw a Karnaugh map. If you're trying to draw a 5-variable Karnaugh map, it will take up a lot of space, not to mention 6 or 7 or any further larger expressions. And that's all for the video on the Quine McCluskey method. Thank you for watching.